So,
Yeah, so welcome to Fire Tie Radiation. This is the 14th session, and today we'll resume with mechanics again. And we could not get Diksha to come, she had some exams. So we will only be doing mechanics like last time, and Kishore will do it for us. So, Kishore, please.
okay, thank you, Atul. So last time we tried to prove that this angle phi naught and this angle phi naught they are same, and so we resume it from here. So now instead of E and M, the constant that we will be using this time will be rho, the closest approach, and V infinity, the speed at infinity. We call rho as the impact parameter. This is the perpendicular distance of the center from the velocity at infinity. So it's not the distance approach, closest approach. Now uh, we use this rho and V rho because they are more natural to the problem. So we can write that E equal to half mv infinity square because we assume that the potential at infinity is 0. And we write capital M equal to mv infinity rho, which looks like the angular momentum. Then this angle phi naught can be calculated as rho by r square dr divided by this quantity. So that does it then. Uh, so this equation they give us chi as a function of rho. Now, should we derive like how do we get this equation, Atul?
Phi naught, that is from the section on
So
what
so
is it called?
so we
Spherical motion? No.
so we have this prior
Circular motion.
no, so we have this prior result, and I think
Yeah.
we need to substitute just uh,
E and
v in
M.
place of e and rho in place of m, right?
Yes. Exactly. Yeah, yeah.
So we get rho by r square dr, and this is 1 minus. Okay.
Or do you, oh,
So
you're saying you want to do the algebra now?
yeah, I was just wanted to prove them also. So it's
Yeah,
a
we can do it. Take a minute. Let's do it. Excuse me. Okay. So I am I think it should be the last term in this should be 2u by m square v square, according to my calculations.
Uh, so, so you got it like rho by r square and v naught. So I think v naught right side, v into r square and v square by r square. Hmm. Yeah, looks
No,
like
also the factor of 2. Oh, no.
Arthur.
Yes.
So I think I am missing a factor of 2.
Array,
So
you
there should
forgot
be,
to multiply 2m with u. That's why. It's correct. It's correct.
yeah, there is 2u. So, but there should be one more thing like 2 rho square by r square. This factor here. Oh, 2m is common. Okay.
Yeah, 2m is common. It's correct. The expression.
Yeah, no problem. Yeah. So, makes sense.
Okay, cool. Let's go on.
Okay, so that's it. So this equation gives us chi as a function of rho.
But how does it give us chi? Because 2 phi naught plus chi is pi, is it?
2 phi naught plus chi is pi. So
Yeah, okay.
yeah, so we get a phi naught as a function of a rho, and effectively we get chi as a function of a rho.
Okay.
So motivation. So physically we are concerned with problems involving not one but a beam of particles, identical particles, incident with a uniform velocity v naught, v infinity.
Okay.
Uh, Different particles have different scattering parameter and are thus scattered through different scattering angle chi. The
Okay.
scattering parameter by that distance rho, right?
Rho. That
Okay.
was impact parameter.
Yeah, impact parameter. What is the scattering parameter?
I think scattering parameters includes both V and rho, or E and rho, whatever.
Okay, scattering parameters.
I
Okay.
don't know. You can maybe look it up if there is a more precise definition. I don't think it's anything.
Yeah, it's a scattering parameters. So, like, you're correct. Like, it will include both V infinity and rho.
Okay.
Okay. So, let dn be the number of particles scattered per unit time through angle between chi and chi plus d chi. So, this number itself depends on the beam density, thus unsuitable for describing the scattering process.
Kichu, can you read it again? I would like to understand it more.
So, this number dn is the particle scattered per unit time through angle between
Through unit area. No.
uh,
Per unit time through, sorry. Okay, number of particles per unit time scattered through angles between chi and chi plus d chi. So this is dn. Okay.
chi was this angle, right? The
Yeah,
this r and chi plus d chi. So in this small window per unit time, how many particles get scattered? That's what we are measuring using dn. Okay.
yes.
So this number itself depends on the beam density. Yeah, that's right.
Yeah.
Thus unsuitable for describing the scattering process. Why?
Because you want to characterize the scattering, so it shouldn't depend on your. I mean, it should only depend on the potential that is doing it, not on how many particles you throw at it and so on. I mean, so it is like if you and I both perform an experiment and we want to see if the thing that we are scattering off of is the same, then we would want a quantity that doesn't depend on how we perform the experiment.
Yeah. Mhm. So let a small n will be the number of particles passing in unit time through unit area of the beam cross section. The beams assumed uniform over its cross section. Okay. So in this case, you assume uniform density. Yeah. So particles passing in unit time through unit area of the beam cross section. further we did like d sigma equal to dn by n. So effective scattering cross section. So did you understand the physical meaning of a small n?
I was trying to think. So I think it's just saying that you take a unit and you look at how many particles go through that unit area in a given amount of time or in unit time. So that will basically, this number will grow if the density of the particles is increased or if the velocities of the particles are increased and so on. And then since your dn, the number of particles that were scattered between angle chi and chi plus d chi will also be proportional to this. Therefore, when you divide by it, you expect that this thing should be independent of your density of the beam and your initial energies.
We want d sigma like, so d sigma will be the scattering cross section. Okay, so unit time
Yes,
to unit
it is the number of particles scattered through the angle chi plus d chi. I mean, scattered between chi and d chi per unit time,
divided by number
divided by
of,
the number of particles that were coming from a given cross section per unit time.
yeah. So basically you rule out the particle density.
Yeah, but that is the idea. Yes.
Yeah, yeah. So from there you get the d sigma, which is the effective scattering cross section. Okay.
Yes.
So this thing will have the dimension of area. Can I see
Okay.
that?
Yeah, let's verify that.
Yeah, yeah, because this is between angle chi and chi plus d chi, and this is through unit area.
Okay. So
So this thing will have the dimension of, because this is a small n will be per unit area. So you will have dimension of area overall.
and unit time gets cancelled and the other thing has no dimensions.
Unit will get cancelled, and yeah,
Okay.
and here it's yeah. So it is entirely determined from the form of the scattering field. Yeah, that's right.
Yes.
Okay.
I mean, I don't know how to make that claim exactly. I can only say that intuitively it makes sense that we've removed the dependence on the number of, I mean, the density of the particles and so on, but I don't know how you can make that statement explicitly. But okay.
Yeah, so like if it does not depend on the particle density, then
It could be that
clearly
this
we can
depends on n square or something, no?
n squared.
I mean, how do you know it depends only on n and not some polynomial in n?
Because dn does not depend on n squared. Like the dn depends on particle density and like not particle density square and such thing.
No, how,
So we
that's
know
what I'm
about
asking.
dn
How
and
do
we
you
know
know that?
about Atul, the way we define d capital N and
Huh?
small, like from the definition it follows that d sigma will not depend on the particle density or anything. So
Arey, yaar, Kishore, this is, I don't think that is correct. I think you can, in fact, I mean, I can't think of a counter example directly, but I think even if you have a, so if I ask you what is the number of particles that, yeah, okay. So if I have something like number of particles that have neighbors, or I don't know. So number of neighbors or something if I have, then that would depend on n square or something like that, right? So it that also has the notion of number of particles, but it could depend on the square or something like that.
I don't know how to like relate it to what we are talking about.
I think I'm not able to think of a proper counter example, that's why. But I understand your point. You're trying to say that since both of these things are explicitly referring to the number of particles,
Yeah, yeah.
therefore they would have no n square dependence. It should depend on n linearly. I agree with that, but I mean intuitively I agree with it, but I'm not sure if that is enough. Anyway, okay, let's proceed. It's okay, no problem.
No, what I was saying, we know the dependence on Dn on all the parameters. So this thing is a complete description of D of capital N, and this thing is complete description of small n. So D sigma will be the complete description of Dn by D small n. So that's what I'm saying. There is nothing missing and all. So
No, it's not about missing. It's about you're putting some constraints, right? You say number of particles that are doing something. So when you say number of particles that are doing something, in that it's possible that the number of particles, uh, the dependence that you get is not the same as linear dependence on the initial density of particles. That is all I was saying. Because you're putting constraints, no? It's like saying number of particles that have neighbors or something like that. I was just trying to change the constraint, but I can't think of a counter example. That is the problem at the moment. So, but it's okay. Let's go on.
okay. Assumption: the relation between chi and rho is 1 to 1. This is so if the angle of a scattering is a monotonically decreasing function of the impact parameter. So chi and rho is 1 to 1. This is so if the angle of a scattering is a monotonically decreasing function of the impact parameter.
So how do we get this chi? So we had an expression for theta as a function of rho, right?
Theta is a function of rho.
So we can convert that to chi as a function of rho.
Yeah.
Okay, can you? Okay, I'll just check. Okay, so phi. So that was pi minus 2 phi naught would give you that. So
Yeah, pi minus 2 phi. So if rho increases, pi minus 2 phi naught will decrease, should decrease if it's monotonically decreasing thing. So if phi naught is a monotonically increasing function of rho, then we are done.
but that is not obvious, is it? If phi naught is a decreasing function.
Phi naught is a
No.
increasing.
So if I increase rho, the denominator gets smaller and the numerator gets larger.
Denominator gets
If I increase rho, since you're subtracting it from the denominator will get smaller if I increase rho, correct?
yeah, and the numerator will
And
become
since I'm increasing rho, the numerator will become larger.
yeah,
So
numerator
that
will become large.
entire expression will increase if I increase rho.
Yeah. So phi naught increases when so phi naught is an increasing function of rho. So 2 pi minus 2 phi naught will be decreasing function of rho. So
So that should establish the result.
yeah. Okay.
But there is this thing about 1 to 1, which we I think have glanced over. The relation between chi and rho is 1 to 1. This is so if the angle of scattering is monotonically decreasing function of impact parameter. Oh, okay. But where did we didn't have any 1 to 1 thing, right?
If it's monotonically increasing or decreasing, then it will be 1 to 1, right? If it's not just increasing or decreasing.
That is true. Okay, but then why is it saying this is so if the angle of scattering is monotonically decreasing function of impact parameters? We already established that, right?
You mean to say that there are cases when it's not a monotonically decreasing function.
Well, this seems to suggest so.
Yeah.
Because it says assumption, right? It doesn't say claim or something. Or maybe Landau does write it as a claim and I didn't understand. Could be. Anyway, okay, let's go on. Let's see what happens.
Okay, so claim is in that case then only those particles whose impact parameter lie between rho chi and rho chi plus d rho chi, are scattered at angle between chi and chi plus d chi.
Okay.
So yeah, makes sense.
Yeah,
So
yeah.
number,
Because
yeah, because it's monotonically decreasing function. So number of such particles equals dn equal to 2 pi d rho into small n. Um,
D rho is the area.
so 2 pi d rho will be the area between circle of radius rho and
Circle of radius rho plus d rho.
so can I look it from the diagram? So
So think of it as the.
rho plus d rho.
So remember, this is symmetric about the z axis or whatever this axis is.
OA axis.
Oh no, no, not that. It is also symmetric along the. So the axis, the horizontal axis, with which contains O,
Mm-hmm.
because it's a central potential, right?
Mm-hmm.
So it will be symmetric around the horizontal axis which contains O. So therefore, you take a radius from the axis, a distance rho, and that circle will give you the same scattering, same chi's. Make sense?
Yeah.
So that is why they're looking at an area I mean, area enclosed between a circle of radius rho and rho plus d rho, which is 2 pi d rho. Sorry, 2 pi rho d rho.
Yeah, 2 pi rho d rho. Mm-hmm. 2 pi rho d rho.
Okay, so you have 2 pi
So
d rho into the density, the number of particles per unit time per unit area.
so you call that
Yes.
so number of such particles equals dn. Okay. So small n. From here you get 2 pi d rho into small n. Where is rho then?
2 pi rho d rho into small n.
Yeah, yeah, yeah.
And
And you write that
on one line I missed a
one
row.
is
I missed a row. That's wrong. It is 2
okay.
pi rho d rho into n. Look at the next
Yeah,
line.
yeah, 2 pi. So from here we get d sigma equal to this thing divided by small n
Yes.
d rho.
Yes.
So note that rho is a function of chi. So you know the effective scattering cross section for a given chi plus d chi range. Okay. So
So you
d
can write
sigma we
rho as 0 by d chi into d chi. That is okay.
so we write d sigma is 2 pi rho as a function of chi into d rho by d chi into d chi. So this is d rho by d chi usually the
Is usually
subtle
negative.
point.
It says d rho by d chi is usually negative. Subtle points are there in the book.
D rho by d chi is usually negative.
That we saw, no, that it's a monotonically decreasing function.
Uh-huh.
But why is it usually a monotonically decreasing function, that we don't know. So those are probably the subtle points in the book. We can probably look at later. Kishore, something got stuck. I can't see anything moving.
Yeah. No, I was not moving it. Okay. So
Oh, do we
convention.
have a problem?
What?
What happened?
No, I was just thinking about this thing. So
Oh, what is it? It's okay, right? The
yeah,
expression?
I was thinking what's subtle and all here. Okay, anyway. So
Oh, I don't
convention.
know, yaar. Usually I think it has to do with the fact that it may not monotonically decrease.
Mm-hmm.
So That I don't know how to fix.
Okay. So often d sigma is referred to the solid angle element d naught instead of the plane angle element d chi. Okay. The solid angle between cone of vertical angle chi and chi plus d chi will be d naught equal to 2 pi sine chi d chi.
What's the definition of solid angle? What was it? Area upon volume upon area, something else. No.
Solid angle was no, solid angle.
Right? So something like that. No, you take a sphere and you take volume and
Let's
divide
think
it
of a sphere. So in the case of a sphere, 4 pi r square will be the uh, 4 pi r square will be the what do you call the surface area of the sphere, right? Atul?
Yeah, sorry, it got. I accidentally went away from the tab, and my system has this application that kills tabs when I don't look at them for some time. So, sorry.
Okay, so for the sphere, uh, the if we 4 pi r square is the surface area, right?
It is surface area divided by r square or something. No,
Surface area divided by r raised to power d minus 1, I guess.
d is the dimension, right?
Yeah, yeah.
तो फिर वही है, ठीक है, correct. Let me check.
Uh,
So surface area is what? Uh, it says it's 4 pi into d sigma uh, by a into r dot n cap. अबे यार क्या लिखा है? Pyramid. Okay. हाँ ये रहा. Solid angles in arbitrary dimensions. 2 pi power d by 2 divided by gamma function d by 2. अबे यार रुक. ये बोलता है solid angle in steradians equals the area of the segment of a unit sphere in the same way a planar angle in the radians equals the length of an arc, that of a unit sphere. Okay, so solid angle equals the area segment of a unit sphere in the same way in radians equals arc of a unit circle. Okay. That is the intuition. Okay. So for a unit circle, what will be the equivalent circle? Okay, the solid angle of a sphere measured from any point 4 pi r. Okay. ठीक है, what you were saying was right, Kishore. Then you just calculate the area uh, from the. So calculate the area of that object from whatever is your coordinate system, assuming that is spherical. Just find the area and divide it by r square. So what you were saying was correct. It's surface area by r square.
so,
So
like in technical terms, how do you define it?
So the best intuition I could understand was that so how you define an angle is as follows. You would say that the angle is so if you have an arc, then the angle of the angle the arc makes is the same as
Length divided by r.
so basically what you say is that the sense in which the arc is the same as the arc of a smaller of a circle with unit radius.
Mhm.
That is basically, in what sense it's the same? It's the same in the sense of an angle, right?
So solid angle will be the area.
Yeah. So in solid angle, they say the area of the object should be the same as become same as as that property of a sphere with this
Yeah,
with unit sphere of some area, and that
yeah,
property happens to be you take the surface area divided by r square.
yeah, yeah.
So in polar coordinate system, it's just sine theta d theta d phi.
Mm-hmm.
So okay, so how does it come here? It is sine theta d phi. Now phi can go from 0 to 2 pi, and sine theta d theta. Do you see it?
Yes. Where?
The solid angle d naught is 2 pi sine chi d chi. That is fine, right?
Yeah, yeah, yeah.
Okay.
So d
Okay.
sigma will be rho chi by sine chi into d rho
Mhm.
by d chi into d naught. Yeah. Hmm. So now back to the problem of scattering of a beam of particles, not by a central field, but by other particles initially at rest. So the
निकल
claim
रहे
is
हैं
that
ना, जरा जरा सा दिखा रहे हैं।
what?
थोड़ा मतलब स्क्रॉल नीचे कर ले थोड़ा और। हाँ,
Okay.
ज़्यादा हाँ।
So we turn back to the problem of, so we are back to the problem of scattering of a beam of particles, not by a central field, but by other particles initially at rest. So claim is that the effective cross section as a function of phi is given by d sigma equal to 2 pi rho d rho by d chi into d chi in the center of
Hey,
mass.
Kishore, one second. No, Kichu, 1 second. So now what is the problem we're doing? We're trying to find
Yeah,
the
here is
scattering
the
of a
central
beam.
field. Now we are talking about, we have some particles which are initially at rest, and in the presence of those particles, we are looking for the problem of scattering of a beam of particles.
Okay.
And we assume that the uh, in the center of mass system, the effective cross section as a function of chi will be given by this expression, d sigma equal to 2 pi rho d rho by d phi d chi. Now, I don't understand like how it makes sense.
As a function of I.
So
Okay, let's read the tip. Maybe the tip will help.
what's it again?
The the hint given in the text. What does it say? To find the effective cross section in terms of theta,
Lab
lab
frame.
frame, the relation derived between chi and theta can be used. To find the effective cross section in terms of theta, the lab frame, the relation derived between chi and theta can be used. Effective cross section in terms of theta in the lab frame. So instead of chi, they're asking us to write it in terms of theta, and we know already the relation between chi and theta, no? Or is it something else? So did we do something like, I think in the previous lectures we did something. We had a relation between chi and theta. Oh, yeah, Kishore, I'll tell you what, it will make perfect sense once you're able to write a summary of what we've read.
Okay.
Because what we did in the previous sections was we related chi with this very theta,
Mm.
and that chi is still the same. Kichu,
Yeah.
are you there?
Yeah. Yeah.
So if you look at the previous sections, no, there we have a very special meaning of chi.
Mhm.
Velocity of the particle after, I mean, in the lab frame, I think, oh sorry, in the rest frame, with respect to the initial velocities in the center of mass frame. And that chi is the same as the chi we are considering now. So, and we already derived a relation between, so if two particles collide, or I don't know, n particles collide, we already found a relation between chi and theta. So, so I think this part will only get clarified once you help us revise everything we've done. Are you there, Kishore?
Yeah. Yeah. Mhm. So, and so what should I do? Like move forward? Atul?
Move forward. It's okay. You have to clarify this next time. I should write it down. Clarify page 6. Okay.
So this gives the scattering cross section for the incident beam and the particles at rest. Same expression in terms of theta 2.
And this part you will clarify next time. So let's go to Rutherford's formula.
So now just do this thing the Rutherford formula. So introduction. For an application, what? For an application, consider the scattering of charged particles in a Coulomb field. We put U equal to alpha by R in the prior result of the what section? Previous section,
Previous section.
and integrate to find phi naught equal to this quantity. And from there we can find rho square equal to this thing.
Let's integrate now. I've not integrated in a while.
So like we want to do it. So
Yeah, it says verify this, which means I did not do it at that
E
point, so which means I should
alpha
do
by
it.
R. So we have equal to alpha by R. Okay.
You have to tell me how you do it also because you are really good at all these things, I remember.
What?
JE Bugger.
Sorry.
So now what is the form of U that we have to take?
U alpha by R.
So what, you have to complete the square or something?
Mm, looks like what to U by R, right? U alpha by B which is square R. Okay. So
So A plus 2AB.
Actually, if this thing were plus rho square by r square, then things were better. But it's minus rho square by r square. So completing the square will not make sense.
Okay, if you say so, I have no. Why won't it make sense? What is the reason that you gave?
Because then you do, okay, you can still do something minus square. Yeah. Because this thing has 1 by r and this thing has 1 by r square. So you will do constant minus square. Earlier I was
Yes.
thinking square something, but that will not make sense because uh, here it's minus in front of 1 by r square.
Now you can take the minus of the whole thing, no? That.
Yeah.
Okay, Kichu, were you able to do it? Otherwise, we can do it next time.
Did you do it?
No,
Huh?
no.
So so I got
Let's
something like 1 by x square dx divided by under root constant minus x square.
say it again. One by.
So the form is 1 by x square dx divided by under root constant minus x square.
That I also got. But just that in the numerator, I don't have a 1 by x square. I have some constant by x square.
Yes, it will be shifted basically. I was talking about the form. So
Yeah. So, so 1 by root of a square minus b square is some cosine inverse integral, no?
1 by
What is the integration of 1 by a square minus b square? A square minus x square.
1 by under root of a square minus x square is sine inverse of something. Sine inverse of x by a. So it will be, yeah. So we will get sine inverse. Yeah. So from there you can get write it in terms of cos inverse because pi is 2 pi minus phi, pi minus 2 phi, right?
2 pi minus, 2 pi minus 2 phi
Yeah,
naught
pi,
is equal to
pi, 2 pi minus 2 phi naught.
no, it's 2 pi minus 2 phi naught, right?
2 pi minus 2 phi naught. No, pi minus 2 phi naught.
Phi naught is equal to half pi minus chi, or you can write as, I don't know, up to you, I mean, whichever way.
Yeah, divided by C by x square minus 9. still, like if it were x divided by under root constant minus x square, then it were better. But it's 1 by x square, so we can't like get the form sine inverse.
Yeah,
X
but
by
if you
x.
put the 1 by x square inside, no, you will get constant.
Uh,
Okay, never
the
mind. It's taking too long here. Let's do something. Sure.
uh, okay. So we write phi naught in terms of rho, and from there we get rho square equal to alpha square by m square v naught v infinity 4 tan square phi naught. And using phi naught equal to half pi minus chi, we get rho chi square equal to alpha square by this quantity. Okay. So differentiating this with respect to chi and substituting in the scattering cross section, we get so
ठीक है ना? Because you had a d phi d rho by d chi. No.
d
You
sigma
had 0 by d phi into d phi. Yeah. Okay. What was the expression there for the? Okay. So d sigma rho by sine phi. It's 2 pi rho d rho by d rho d rho basically. Okay. Okay. All right, Kishore. What happened?
I was drinking water.
Oh, sorry.
So we write rho square as rho square phi by 2. Like you are like trying to find how we got here. Atul?
Huh? What?
So what are you are trying to find d sigma.
I was looking at the expression for d sigma. That is just 2 pi rho d rho. So you can write it as d rho by d chi into d chi. That is also fine. So you can just differentiate rho square with respect to chi, and you will get that expression. So okay,
Yeah.
basically Rutherford's formula. Okay, fine. Okay, cool.
So just a moment. So d sigma was 2 pi rho d rho. Okay. So d sigma by d chi. Okay. So 0 by d chi. D chi will be given d sigma. Okay. So from here we get d sigma, and we write d sigma is this quantity. This is the Rutherford formula. Ah. Sine 4 pi by 2. Yeah, I remember this thing like from particle physics,
What do you remember? I
right?
don't remember.
Particles.
Mm.
Yeah, we had cosec to the power 4. Yeah. So it's 1 by
There was
sine.
something. Yeah, we did something. Something like that.
Yeah. So note, the effective cross section is independent of the sign of alpha. So the result is equally valid for repulsive and attractive Coulomb field.
Yes, makes sense.
Yeah.
No, actually, I don't know if it makes sense, but
So yeah, because it's squared.
I meaning physically silly. Of course, from the formula it is squared.
How it makes sense. So even if particles are attracted or repelled, don't you think the trajectory will be symmetrical with respect to some axis if particles are attracted versus repelled?
Yeah, it should be symmetric, I suppose. I'm not sure.
Like Just in case that in one case the particles go upward, the other case they will go downward.
It's not so obvious, no, because in the case they're going downwards, the distance is decreasing, and so the attraction will increase.
Yeah.
So the other case they're going farther away, and the repulsion will decrease. So you know,
No, but I think you are assuming that when they are going down, their closest distance uh, decreases. I mean, the going up and going up or going down that happens when they are at the closest distance, closest approach. That's what I'm assuming.
I don't know. I mean, it's far from obvious for me. I don't know how it's obvious for you. I can't even see. Anyway, okay, let's just
Yeah.
look at the final formula more carefully, what all it has, so we can, maybe get some more intuition.
Okay. So the effective cross section is independent of the sign of alpha. So the result is equally valid for repulsive and attractive polar fields. Again, as before, d sigma is given. Uh, what is this?
For no, I don't know. Given,
Again, as before, d sigma is given.
I don't know, yeah, what I've written. It's an F with a O. I don't know.
in the in the center of mass frame of the colliding particles. To obtain the corresponding d sigma for the particle at rest, we use chi equal to pi minus 2 theta 2. Okay.
This stuff you will have to help us recall, yeah, because I know what is theta, but how is chi the angle of the center of mass? That I'm not sure. Yeah, that this party will have to help us revise from the discussion of one particle, two particle collisions, and so on.
Mhm.
Okay. So I suppose this is just some calculation which we can, for the timing, assume. And
So from there we get the d sigma. D sigma 1 can also be found. What is d sigma 1 and d sigma 2?
it depends on if you are resolving chi with respect to theta 1 or theta 2.
And what about theta 1 and theta 2?
Theta 1, theta 2 were the angles of the particles with respect to, I think, the z axis or something like that.
Uh,
In the So you remember there were, when two particles collide, then we have these angles thetas, right, that were defined for the general case. So
theta
initially he
1 and
discussed
theta.
the disintegration of particles, in which he said that the angle after they disintegrate, the angle they make with the initial velocity of the center of mass was called theta naught in the lab frame and theta in the other frame. And then they had something similar with two particles. Theta 1, theta 2 were what? Let me see.
The
Then
angle which they make with the initial velocity axis.
something like that. But yeah, so so the relations were not as straightforward always. So theta 2 was simple most of the times, but theta 1 could be more complicated.
Mhm.
Yeah. So theta 1 in some case becomes half of chi, theta 2 is just half pi minus chi. And yeah. Anyway, so this part you will have to revise, Kishore. This is a chapter with a lot of small results which have to be kept in mind. So let's go on. Okay.
So, so d sigma 1 can also be found, but the result becomes complicated. So we discussed two particular cases. First case when M2 is much larger than M1, then chi is approximately theta 1 and M is approximately M1. Then d sigma 1 will be, okay, chi is theta and m is m1. So this thing will be alpha by 2 m1 v infinity square d. What is do? So
That is solid angle d0. Sine theta
solid
d theta d.
sine for, yeah, sine for theta 1 by 2. Okay, where you define E1 as half m v1 infinity square. Okay, so when case m1 equal to m2, that is a small m equal to small m1 by 2, then prior result, that is theta 1 equal to chi by 2 is obtained. Okay, can I see that? Uh,
What are you trying to see, Kishore?
this thing theta 1 equal to chi by 2.
Yeah, that is, I don't know where the expression for theta 1 and chi is. That's why I'm saying there are a lot of results. No, theta and chi were there for many different situations. So you'll have to look at it carefully. So for example, on page, what is this? Just before page 5, it says that in the special case when m1 is equal to m2, you can write theta 1 equal to half of chi. So,
Okay.
and so in general, it's not so simple because the
Okay,
relation
anyway,
between theta
so
1 and chi involves sines and cosines and things like that. And so it's not always obvious.
mhm.
Yeah. So for example, theta 1 is given as tan theta 1 is equal to sine chi upon m1 plus m2 cos chi. And that we derived using some simple trigonometry. It's not hard, but you know, it's okay. Let's go on. I'm just telling you it's okay.
So from there we get d sigma I1 equal to 2 pi this thing uh, cos theta 1 d theta 1 divided by sine q theta 1,
Yes.
and
And then you
from
just put
there
a solid angle, so you get a sine theta extra downstairs. That's all.
we just get sine 4 theta 1. Okay,
Hmm.
so really that if the particles are identical, the incident and the one at rest, that is, then the total effective cross section is the sum of d sigma 1 and d sigma 2, and replacing theta 1 and theta 2 by their common value theta. Okay.
This is clear if we look at the result after transformation to the lab frame. However, I'm unclear about the result's validity if I start from d sigma of chi. Well, anyway, so then d sigma is equal to alpha by e1, 1 by sine square plus 1 by cos, sine 4, 1 by cos 4 into cos theta d sigma. I think we will have to understand the
Relation
theta.
between theta 1, theta
Yeah,
2, yeah,
it will stop making
sigma and
sense.
all. Okay. So claiming that the uh, energy acquired by M2 and
Achha,
uh, lost by M1.
understand array or let us stop at this stage, either of the two, because it will stop. It's not making any sense for me without understanding theta 1, theta 2. It's becoming useless. नहीं?
Yeah, you're correct. Yeah, हाँ सही बोल रहा है.
So we can let's try to do it next time then. And like next time we should
Okay.
be able to finish it. It's just one more page. So we should
Yeah.
make a summary of all of this first and then try to revise it. Otherwise, it's not
So
worth
right
it.
now we are in chapter 4, right?
Yeah, chapter 4, just the last page is left after this.
Okay.
So, okay, so I'll get this back. Thanks, Kishore, for your presentation. And I don't know if you have anything to add at this stage. Otherwise, we can just
Thank you.
Okay, brilliant. Okay, so let's stop it here. Next time we'll hopefully have Diksha, and we can also do some quantum field theory, and we'll revise this the overall chapter and finish the one section we couldn't do, and hopefully we'll be done with chapter 4 next time. It's been a long time. We can move on to chapter 5 over. So, all right, have a good time. See you.